Okay, good afternoon, everybody. So, yeah, I've mentioned probability several times, but we have not really talked about it. So I want to cover at least one probabilistic approach, which has to be the Bayesian approach, just because of its history and performance. So we want to see how much we can cover. Hopefully we can cover the Bayesian approach today and on Thursday. And next week, I usually have the past 2-3 years, we have dedicated the last 2 lectures to ethics. And then the last quiz is always about ethics. So if nothing changes, the next week will be the 2 lectures about ethics. But at the moment, I'm also thinking, because we have never really talked about how to write a paper and what are the expectations. So we want to do that next week somehow. Maybe the last tutorial. Maybe I do the tutorial myself. We will see. I'm still talking to the TAs. Okay. So we want to talk about Bayesian learning. And just refreshing our minds, we were talking about that we have imperfection. And imperfection in data is the reason that we are doing AI and some other stuff, of course. And imperfection has fundamentally 2 sources. Some people may say there are more than 2 sources, but I would say you can put any of them in one of these 2 categories. One of them is vagueness. And we talked about fuzzy logic as one of the major platforms to deal with vagueness. And we talked a little bit about fuzzy sets and entropy and inference and rules. We should have a vague idea of what fuzzy systems are. And we have uncertainty, which responsible for that is, of course, the almighty probability theory, which is, well, depending on when you start looking at things in the history of science as probability, 300 years old, maybe more. And so we have talked a little bit about this, not much this. Of course, probabilistic approaches are a major part of machine learning. So we want to talk a little bit about them. So at least one method, maybe 2. So again, even if you want to talk about probabilistic approach, you still have a universe of discourse. So U is your universe of discourse, which is basically what is the range of your variables. So where are you moving? So then we have an A, which in contrast to the fuzzy sets is not a fuzzy set or is not a subset. A is a set, or rather event, that is a subset of your universe of discourse. So I would rather say event, but we cannot totally exclude sets, because for a long time, because we didn't have any other tool, even if it was explicitly a set, we would still use probability theory because we didn't have anything better. So we had the only tool we had to deal with imperfect data was probability. Now we have another tool. So the art is just, okay, just distinguish. Is it this or is it that? And of course, you have a variable x, and this variable, which could be a random variable, belongs to A. X belongs to A. Okay? So I want to just maybe a little bit review that again and go a little bit more detail with respect of when we write a number between 0 and 1, and these 2 people fight each other. One says is a membership, the other says is a probability. So what is what? Most of the time, they don't know each other. They just have some prejudice of each other. So as engineer, I don't care about their academic fights. I want to have tools. So I try to say, okay, so this is good for this is good for this. You can continue fighting. I want to use both of you. So what is that? So basically, we want to see what is the difference between the probability of set A or event A and the membership of X to the set A. So what is that difference? But because both of them are between 0 and 1. So you see numbers between 0 and 1. And to this date, people look at it from, well, you have to imagine this. This is a young guy. This is a very powerful old guy. So he knows a lot of people. This guy is still developing. So, okay. This camp is much larger than this camp. So, okay. And the confusion is sometimes justified. You are working on numbers between 0 and 1. Why are you calling them this or that? So can you justify it for me? So when we talk about the probability of an event, what is the probability of the event that tomorrow it will rain? What is that probability? What does it say? What does it mean? The probability that I get cancer, the probability that the stock market tomorrow collapses, the probability that after 10 meters my robot encounters an obstacle. You can understand basically anything in terms of probability. And we have been doing that because it's a very powerful tool. So is the probability that the P of A is the probability that an ill-known variable X, ranging on U, the universe of discourse U, hits the well-known set A. So that's what probability means. So I have a universe of discourse which is the set of all days, from Big Bang till, I don't know, till 100 years in future. So that's my universe of discourse. Then I have an ill-known variable X, tomorrow. I don't know what tomorrow will happen. And I want to know how much it will range on U and hit the well-known set A, rainy days. So how can I know that tomorrow, on the range of every possible day that we know, will it hit the well-known set of rainy days, sunny days, snowy days? So that's what probability gives us, which is fantastic. Well, this guy is a membership, the membership of a well-known variable X, ranging on the universe of discourse U, that is hitting or hits the ill-known set A. So it's exactly actually opposite. Why? It's not clear why people don't get this. So here the variable is ill-known. Here the variable is well-known. And here the set is well-known. Here the set is ill-known. So they are the opposite of each other. I would rather say they complement each other. But okay. So we talked about this, that actually this is when the event happens. And this is the best way that you can separate them. So probability here, from here on fuzzy logic. So which means now I know what is happening. Now it is tomorrow. I know it's raining. So the variable is well known. I know tomorrow. Tomorrow has become today. But we are discussing whether that's a drizzle, or it's a light rain, or it's a difficult rain, or it's a heavy rain. So the set is unknown because I want to assign it to the set of light rainy days. And we disagree and say, no, this is not light rain. This is moderate rain. This is a moderate drizzle, whatever. We cannot agree. It's vague. It's not uncertain. It's vague. So very different things. So this one is helping me today This guy will help me tomorrow. So we should not mix this. Can you solve problems of this guy with this guy? Yes. Can you solve problems of this guy with this guy? Yes. Will it be wrong? No. So then why it's better formally that you know what you have, you understand your problem, and you use the proper tool. Otherwise, I can guarantee you, you can take any problem, solve it with any method. You can just shove it down the throat of the problem because I love deep learning, so I want to solve it with deep learning. Okay. Whatever makes you happy. But it's not like that this guy owns or this guy owns everything. So everybody can provide a solution. So this is before it happens. We talked about this a little bit, I know. But this is so important. And this is after it happened. After it happened. So there is a lot of uncertainty here. There is no uncertainty here. Here there is no vagueness. Here there is a lot of vagueness. So if it's today, I don't care I don't want to discuss whether there's a drizzle or storm. I say, will it rain? Because I want to take my umbrella with me. I'm concerned with a very simple problem, which is binary. Will it rain or not rain? I don't care about the intensity, because that does not affect me needing an umbrella. But here, then we are sitting in the plaza drinking coffee and saying, what type of rain was it? So this guy has a real problem. This guy has an intellectual problem, maybe. OK. Now we can continue and say, OK, continue comparing again the probability of the event A versus the membership of X belonging to the set A. Well, this guy is based on measure theory, a very theoretical framework that I don't think any of you has dealt with it in your undergrad. You would have done it if you would study mathematics. So this guy is dealing with set theory. Why we had a little bit of set theory? A little bit. So again, they are very different. So the domain here, the domain of the probability is 2 to the power of your universe of discourse. Why 2? Because things will either happen or not happen. Will my airplane crash? How big is the probability? Well, my airplane will either crash or not crash. There's nothing in between. So things are binary. Things are binary in probabilistic domain. But 2 to the cardinality of set of my universe of discourse, that could be a big space to search. But it can get even worse for this guy. The domain here is the closed interval 0, 1 raised to the power of u. Wow, OK. So I thought this one is difficult. This is more difficult because this continuum, every one of them. OK, whatever the reality is. So probability is based on the Boolean algebra. Again, so this Boolean is binary. Will the stock market crash or not? Tomorrow is there. No, it didn't. So yes or no. It's Boolean. Probabilist. This is so difficult for people who are in the field to get that after a while. Probabilist, you are using numbers between 0 and 1, but you are Boolean. You are binary. You are saying yes and no. It's very different. This guy, everything he says is a matter of degree. It will drive you insane. Anything you say is a matter of degree. I give you 10%. It never says yes and no. So this guy is not binary. This guy is binary. You see the difference? It doesn't matter that your probability value is between 0 and 1 because you make a decision upon that. That decision is binary. So somebody I will go to, I don't know, somebody who has the power to predict the future, and so if I go on this plane, will it crash? And she says yes. So I don't go. because I'm superstitious. So I make a decision. I will not go. You either get on or you get off. This guy cannot be a Boolean algebra. It is not a Boolean algebra. So one thing that hopefully we have learned somewhat is when somebody gives me a problem, I have to find the right tool. So what does it match with? Is it something that I can go with decision trees, fuzzy inference system, a probabilistic approach, support vector machines, k-means, multi-layer perceptron? Which one is it? This is half of the battle. If you go the wrong way, it will cost you a lot of time and energy. So I have to know who is responsible for what type of problems. Is the source of imperfection, and this is all what we are fighting. We can call it anything else. So any challenge in the data is either because of the uncertainty or because of vagueness. If data is missing, it's uncertain. You couldn't get enough data. Okay. So, of course, we have to start with Bayes' theorem. I'm sure some of you have heard it, have seen it. So Bayes' theorem says, okay, I want to calculate the probability of a hypothesis H given data D. So that's what I want to do. So I want to check hypothesis is tomorrow will rain. And I have measurements for Canada for the past 50 years. So that's the task. How probable is it that tomorrow, March 27th, it will rain in southern Ontario? I have a lot of data, and that's my hypothesis. So it's quite intuitive, actually, to use probability theory and Bayes' theorem. So is equal, Bayes told us, is the probability of data given that specific hypothesis times the probability of hypothesis divided by the probability of data. So this is basically the posterior. This is what it should come. This is what has not happened yet. So this probability of data given hypothesis is the class likelihood. This probability of hypothesis is, of course, your prior. So how much you know already? How much you know about days being rainy, days being snowy, stock market crashing? How much do you know about that? And of course, the probability of data is your evidence. So the probability of prior and probability of data are basically opposing each other. And the probability of hypothesis given data and probability of the data given hypothesis oppose each other too. So this is a really nice balance of it to be able to make predictions and classifications and decisions in general based on the nature of data. So if you think there are books. I had one of them when I was a PhD student. My supervisor pushed a book in my hand and said, read this. We will talk next week. And I said, 700 pages. When should I read this? There was only one equation in that book, and that was this one. One equation, 700 pages. And this is not exaggerated. This is one of those fantastic equations that we have. So you can do all sort of things with Bayes' theorem. Okay, let's have an example. So I wanna do medical diagnosis with this Bayes' theorem. Can I do that? Yeah, sure. So meningitis, which is an inflammation of the brain membrane, is a brain disease. Meningitis causes the patients causes the patients to have stiff necks. Stiff necks 50% of the time. So this is one of the things that we know about meningitis. If you're suffering from meningitis, half of the time you have stiff neck. But I can have stiff neck for many other reasons. I slept bad. I don't know. I was whatever. So why it should be? Well, that's the uncertainty part. It's uncertain. We don't know. You can have stiff neck for many, many other reasons, not just for meningitis. So that's the worst case scenario. Okay. So we know, now this is the key word, we know. We know that the probability of meningitis is 1 over 50,000. So 1 out of 50,000 people suffer from meningitis. That's the statistics. That's your data. That's the evidence. So we also know that the probability of stiff neck, given you are suffering from meningitis, is 0.5. So that's what I just said. So if you have stiff neck and you're suffering from meningitis, that's 50% probability. But we also need the probability of stiff neck. So it doesn't matter why, how many people, how much of the time you have a stiff neck. Why? We need to call Statistics Canada and say, have you collected data about how many times people have a stiff neck? And they say, yeah, we don't have anything better to do. That's 1 out of 20. Okay, you see, that's now useful. 1 out of 20. So 1 out of 20 people have a stiff neck for some reason. So now we want to say, okay, what is the probability I have meningitis given that I wake up and I have a stiff neck? So this is a fantastic question. That's diagnosis. That's diagnosis. You go to the doctor and say, doctor, I have a stiff neck. And say, you are suffering from meningitis. I don't think he will say that. Because he or she may not use Bayes' theorem, but they have a lot of experience. So they have a lot of those rules in their head that they apply. So, okay, how can we do this? Well, we just put in. So the probability that I'm suffering from meningitis, given that today morning I woke up and I have a stiff neck, is, according to the Bayes theorem, the probability of stiff neck given meningitis times the probability of meningitis divided by the probability of stiff neck. We have all those numbers. You put it in, you get 0.0002%. Okay, no worries. This is still a much higher probability than my airplane crashes, but okay, so it's not even close to 1%. So I'm not worried about that. Unless my stiff neck just stays around for more than 2-3 days, then I get worried and I do additional tests. So I put all these numbers here. The probability of S of M is given, is half. The probability of meningitis is given. Where was the probability? I did give it that, right? Did I write it? Yeah, 1 out of 20. The probability of stiff neck is given, so we can calculate it. Okay, so, but like any other machine learning technique, you need data. So how much data do you have? What happens if my data is not so singular and just 1 or 2 instances? What happens if I collect data for 10 million people? Well, then you need some systematic way to infer new knowledge. So, okay, that's okay. That's what we want to find out. So what are some basic rules before we continue? We need some basic rules. I'm pretty sure most of you know these rules. I just have to repeat them so we are on the same page. So we have the sum rule, which is what is the probability of A and B? So what is the probability that tomorrow rains? And what is the probability that tomorrow snows? What is the probability that tomorrow rains and snows? Well, in Saudi Arabia, 0. In Canada, 85%. Rains and snows on the same day. If you're around April, that's possible. You cannot exclude it. So I can calculate it. That's the probability of A given B times the probability of B. Or I can also write it as probability of B given A times the probability of A. So you need to know the conditional probability, otherwise we cannot calculate that. So we cannot calculate what is the probability that tomorrow rains and is rainy and sunny at the same time. What is that probability? So then I need to know what is the probability that is raining, that rains, given that it's sunny. That's a very tiny probability. Most of the time you cannot have sun and rain at the same time. But there are constellations. One corner of the sky opens up, the sunshine comes through, but it's still raining. But that probability is really, really small. But that's a conditional probability. I have to know that. So you have to make that additional measurements and observations. Challenge of any machine learning technique. The product rule. So what is the probability of A or B? So what is the probability that tomorrow rains or the sun shines? It has to be a larger probability because if they are independent, so I would say intuitively, I would just add the probabilities. So probability of A plus probability of B. But what happens if they are conditional upon each other? Then I have to subtract minus the probability of A and B. Because if they are depending on each other, I can just... So the probability of that tomorrow rains is 80%. The probability that tomorrow the sun shines is, I don't know, 70%. 80% and 70% is 150%. Something is wrong. Because you are not considering that they may be conditionally depending on each other. So I have to take that into account. Do you have those measurements? Okay. So we generally call this junction, and we call this conjunction. Just don't freak out when somebody says, yeah, I'm using a disjunctive rule. What is that? It's just A or B, A and B. And then there is the concept of total probability. The concept of total probability says the probability of B, I'm just grabbing B, is the sum of the probability of B given A sub I times the probability of A sub I. I goes from 1 to n. And A1, A2, up to AN are mutually exclusive with the sum of the probability of A sub I is equal 1. I goes from 1 to n. I'm not sure there is anything more important in probability theory than this. One big normative thing is the probability of all events in my universe of discourse. That probability is 1. Do you remember the biggest sins of fuzzy logic, that they violated this, the excluded middle? So if I take everything, that's everything. So I have sunny day, I have rainy day, I have snowy day, I have overcast. What is the probability that any of them happens? 100%. Do you know any other type of days? I don't. It can be sunny, it can be rainy, it can be snowy, it can be overcast. So that conditional that probability that everything sums up to 100%, it makes our life so easy. Everything has to sum up. So if I assign a class membership of 80% to this class, and I have two classes, automatically that instance belongs to other class 20%. I don't need to make any other calculation. Of course, because everything has to sum up to 100%. This has a problem. We will not be able to get to that, but this is a problem. This is one of those naive things that we assume. This is one of those things that Bertrand Russell said, our mathematics is not made for this complicated world. It's a math for an imaginary world. But it's working. As an engineer, I don't question things when they are working. So the system is working, don't touch it. And if it's not working, first do a restart and see what happens. And if the restart doesn't work, okay, then I sit down and do an analysis. Okay. So things are getting interesting. So again, just don't forget, probability theory has brought us to the moon. If that wasn't a hoax. But if it was real, it was amazing. So I don't know. I cannot verify it. I see the images and say, wow, that looks great. Okay, so what is the idea? What is the idea of the Bayesian learning? Intelligence is to find the most probable hypothesis. Given the training data. Of course, I need training data. So intelligence is to find the most probable hypothesis given the training data. So what is the most likely outcome? One of the things, I just came back from a conference, one of the things that, I don't know why doctors are asking for this, but one of the things that they are asking is the probability, can AI give me the probability of survival of the patient if we apply this treatment? If I do chemo, surgery, radiation, how likely is it that the patient survives? Give me a number. I'm not working in that field. I'm entirely focused on image search, but I find this extremely troubling. Because you want to really trust that prediction, and then what? Change the treatment? What? If it says the probability that we do chemo, surgery, radiation, instead of, let's say, radiation, chemo, surgery, I don't know. There are some financial considerations into this. And says, okay, this one is low. What? We don't do it? Who is going to take responsibility for that? I don't want to take responsibility for that. Very, very sensitive applications. Okay, so let capital H be the set of, let capital H be the set of all hypotheses. So H, capital H, is the set of all solutions. Every possible solution that you can have for your problem, whatever the problem is. There is a set somewhere. In some dark corner of Milky Way galaxy, somebody is guarding those solutions. So we want to find some of those solutions. But we know that solutions exist. We may not be that smart enough to find them, but the solution exists. So the best hypothesis of course, we are going after the best, of course. H star. So let's say H star is the best hypothesis, the best solution. It gives me the lowest error. I predict tomorrow's weather 100 times, and 99 times I'm correct. I predict the survivability of the cancer patient, and 99 out of 100 times after 10 years that we see the outcome, I'm right. So I want the best. What is the best hypothesis? So the best hypothesis, if I find the maximum, the argmax, if I go over all possible solutions coming from the set of all solutions, and I look at the probability of the hypothesis given the data. So that's what I have to do. If I do that, I find the best solution. Things are so simple when we look probabilistic. So if I have the set of all solutions, I can iterate over it. I can do brute force. Let's say I have computational power. I can do brute force. Go over all of them. And then see, I want to find the probability the hypothesis given the data. Probability that I have meningitis given that I have a stiff neck. Probability that I have cancer given I smoke. The probability that tomorrow the stock market crashes given that the federal bank does such and such announcement. Whatever the problem is. So of course then we will say, okay, then I have to find the maximum, the argmax, of every single hypothesis H. And now I write this in terms of the Bayes theorem, the probability of data given hypothesis times the probability of hypothesis divided by the probability of the data, which is the evidence. And of course, this will be the argmax over all possible solutions, the probability of data given hypothesis times the probability of hypothesis. I can get rid of the probability of data because that's a constant. What is changing is the H. The data is, so this doesn't matter. I can get rid of it. The data that you gave me is not changing, is it? So I'm working in the lab. So this would be my perfect solution. But I have to go over all possible solutions. What is all possible solutions? If you are working with neural networks, every possible configuration, 3 layers, 4 layers, 5 layers, 10 layers, 20 layers, each layer having 100 neurons, 500 neurons, 1,000 neurons, 10,000 neurons, I have to check all those solutions that come from capital H, which contains all possible solutions. If H is the set of all decision trees, I have to test trees with 10 nodes, 50 nodes, 500 nodes, 1,000 nodes, 10,000 nodes, 1,000,000 nodes. And then when I find that it's working with 1,000,000 nodes, I have to work, is it working with this way, that way, up, down? You have to still say which attribute is on the top. So that seems to me be a sort of exhaustive search. And we may be able to do that for some applications. Why not? So this is basically H of MAP, which is maximum a posteriori approach, so MAP. So you are going to maximize the a posteriori. So what should I do to get the best outcome in the prediction? So MAP. MAP is clearly something that is, well, it gives you the best result. There's no question about that. MAP gives us the best result. Okay, at what expense? Well, again, you have to try all possible solutions. So it's brute force, yes. So why we are talking about it? Because sometimes brute force can work. Sometimes the brute force is still small enough, we can do it. Don't dismiss it. So I may have an application that with 2 days of computation, I do the brute force. Why not? 2 days is nothing. You just go on the cloud, buy subscription, a cluster of 500 GPUs, I do it. 2 days. I get the solution. 10 years ago was 5 years of computation. Sometimes we can, if you don't see that this is brute force, that's a problem, we have a problem. Because, look, it's checking it for all possible solutions. Which is also actually what neural networks do. They give us the best set of weights among, if you have 500,000 parameters and they are moving between 0 and 1, how many different solutions you have. Can I adjust a neural network using MAP? Yes, you could, if you are insane, because not going to happen. This doesn't. The brute force that we do on the neural network is not actually brute force. And that's the magic of deep learning. How did we do that? How do we do brute force without doing brute force? That's like the kernel trick of SVM. How do you go to higher dimension without going to higher dimension? OK. MAP, fantastic, optimal classifier, but expensive. Yeah, well, for most applications, not for all. For most. If all solutions have the same probability then we can calculate the maximum likelihood hypothesis. So instead of H of MAP, which is exhaustive, if I make a small assumption, which is a big assumption, I assume that all solutions have the same probability. Then H of ML, which is maximum likelihood, is the argmax. Again, I will go to find the maximum over H sub I coming from the capital H, probability of D given H sub I. When the P of H sub I is equal to P of H sub J for all ij's. So I can get rid of that. I can simplify this. I can get rid of this by just now focusing on what is the probability of data given the hypothesis. So we got rid of the probability of the evidence because that's a constant, is not changing, is not a function of the hypothesis. Now we are getting rid of the probability of hypothesis by saying, you know what? Whatever solution exists, let's assume that they are equiprobable. Whatever makes you happy. That's definitely an assumption that is not correct. Yes, we know. But this is another engineering rule which computer scientists and mathematicians have also adopted. If it works, I don't care. So if it works, I don't care that they are not equiprobable. It's working. And naive Bayes that we will talk about is another example for that. We make assumptions that we know they are definitely wrong. But then we see that the method is working. OK. Why you are complaining again? It's working. The machine is working. The airplane is flying. Why are you complaining? Yeah, because it's not. Who cares? Well, in textbook, nobody writes who cares, because that's not just sophisticated to write who cares. But we practically say who cares. Okay. So example. For optimal example for optimal classification. Optimal classification. That's a very dangerous word to use. Optimal. When you say optimal, that means I give you guarantee there is nothing better than this. Nothing better. Be very economical in using that word. Optimal situation. What is optimal situation? I know, you are sitting in the center of the universe and everybody is serving you. What is the optimal situation? It's very difficult to get that. Let's say we have three hypotheses. So the probability of H1 given the data is 0.5. The probability of H2 given the data is 0.3. The probability of H3 given the data is 0.4. I'm assuming that my H is the set of H1, H2, H3. That's what I'm assuming. I'm assuming that I have only 3 solutions, 3 possible solutions, which is a very restrictive assumption. Of course, anything you grab, you have a lot of solutions. Most problems, the more difficult they are, the more solutions you have. But again, you are here, they are on the other side of Milky Way galaxy. You cannot just get to them. But we know that we have solutions. And then we have some new samples. You get some new samples. So that's what you have. That's what you have, right? So you know that the probability that H1 was correct, given your data, training data, is 50%. The probability that the second solution is correct is 30%. The probability that third solution is correct is 40%. This is just to make the point. So this is a network with 7 layers. This is a network with 5 layers. This is a network with 11 layers. This is a decision tree with 500 nodes. This is a decision tree with 200 nodes. This is a decision tree with 1,000 nodes. There are different solutions. Which one of them is? You see, with probability theory, you are operating on the head of other methods. So you are saying who is who. You've got to be very powerful, and Bayes is. So you get some new samples and say H1 of X is positive. H2 of X is negative. And H3 of X is negative. Why positive, negative? Well, again, probability is a Boolean algebra. Tomorrow rains or not? Yes or no? Am I going to die or not? Yes or no? Am I going to be rich tomorrow? Yes or no? So each one of them says something, because they are different solutions. If you give the face to 3 differently trained networks, you get possibly 2 sets of answers. Some of them are right, some of them are wrong. Okay. So which means the set of values that you can get is here simply plus and minus. Binary, SVM, back to the beginning of the lectures. So I gave you some instances. Based on the probabilities, don't ask me how do I got this, because in order to get this, we have to do some work. I said optimal, so I'm making it a really kindergarten example that we can solve it on the board and say, look, if you do exhaustive, and I couldn't say I have 1,000 solutions, because then I have to stay here until tomorrow morning. So let's say we have 3 solutions. And let's say classification is this. How does it work? So then the Bayes optimal classification So the V best, the best value that I can assign, the best class that I can assign to my input is, of course I have to go with maximum, is optimization. I have to go with maximum or minimum, one of them. Of all possibles value V sub j coming from the set of all values capital V. So how many values I have? 2 here. My life easy because I'm working on a Boolean algebra. Things are right or wrong, true or false. Sum of the probability of V sub j given H sub I times the probability of H sub I given the data. And here the sum will goes over H sub I coming from the set of all hypotheses. So now I'm looking at the values. So this is the optimal classifier. And we brought in something like this to make sure that you get the best result. You want to give the guarantee. So how do you give the guarantee? We know that with the probability of Hi given D, we get an idea about which hypothesis is correct most of the time. So, and then with the probability of getting a certain value, yes and no, given that hypothesis, what is that probability? Which is the error. Which is the error of that actual classifier that I'm using. One of them is making more error. One of them is making less error. So, and I want to find that out. So then I have to basically do a lot of calculation, even for this kindergarten example. So I have to calculate the probability of negative given H1. This is 0. The probability of positive given H1. This is 1. What is the probability of negative given H2 is 1. The probability of positive given H2. This is 0. The probability of negative given H3 is 1. The probability of positive given H3, which is 0. So I have to calculate all those numbers based on the data that you give me. A lot of data, a lot of calculations. And again, I just don't have 3 possible solutions. Just think about, okay, I give you even a fixed number of nodes and you want to construct a tree. So how many different ways can you do this? That's infinite. That's intractable. Okay, now I have to add things up. So what is the sum of the probability of positive given H sub I times the probability of H sub I given the data, when H sub I is coming from the set of all solutions. So that will give us 0.5. If I just plug in all those numbers, I get 0.5. And the sum of, again, H sub I coming from the set of all solutions, the probability of negative given H sub I times the probability of H sub I given the data. If I calculate that, I get 0.7. So if my problem was that easy, so here I see that, so the best solution is X is belonging to the set of negative samples, which is the best solution. So are you using multiple classifiers to give me a best classification? Yes. So is this ensemble learning? Sort of. So you're fusing some classifiers together to just eliminate, to combine their forces. Sure. And while you are doing that, I have a limited number of classifiers. Random forest fundamentally works the same way. That's, again, I know I'm being annoying. Everybody cooks with water. So isn't that the same thing that random forest does? The random forest guys stays up in the session, hello, I'm doing this too. No, this is called probability. Who cares how you call it? So you are combining classifiers. But I'm not doing it this way, I'm doing it that way. Okay. But you're doing that. So I'm using, in a very sophisticated way, I'm combining the evidence to exclude, to diminish the probability of error and make a better decision, make the best decision, which is optimal classification. Well, if you could do this in practice, that would be fantastic. Trust me, if I'm saying this, and I'm not exaggerating, we wouldn't need deep learning if you could do this. If you could do Bayes optimal classification. Why we cannot do this? Because I don't have 3 H's. I have 1,000,000 H's. So that's the problem. So I can't do that. It's just computationally intractable. So, okay, then why we are talking about it? Well, to appreciate the practical guy, we have to talk about the imaginary guy for big problems. Not that the Bayes optimal classification is not used at all. We use it. If that space, if the H is small enough, I can use it. If the cardinality of H is rather small, we can use this. And you give guarantee like SVM. Here the guarantee is optimal. Nobody can beat me. Okay. So just imagine for yourself, we want to use an approach like this for face recognition. Not going to work. So not every method is suitable for all possible applications. So, but this is very expensive. This is very expensive, applied on real data, not on my kindergarten example. Applied on real data, that's extremely expensive. That's exhaustive. It works when the cardinality of H is small. So the cardinality of H has to be much smaller than whatever. I don't want to put a number. I don't know. Much smaller than 100. Much smaller than 100. You don't give me 500 decision trees. You give me 5 decision trees. Okay, I can work with 5 decision trees. That's not a big deal. But how do you select those 5 decision trees? How do you select that 10 different configured neural networks? Who selects them? Randomly? But you cannot then guarantee that they are good. Each one of them has to be good. Each one of them has to be good. This probability cannot be 0.001. You're just selling me crappy classifiers? What should I do with that? I need good ones that compensate each other's weaknesses. Okay, so what is the solution? You always do this to me. So you show me something fantastic, but then say it's impractical. Yeah, well, we are working on it. Maybe we find a way. Up to 2006, training a network with more than 6 layers was impractical. So now we can do it magically. What is the solution? Let's go naive. Naive Bayes. So naive Bayes classifier. So we make an assumption that we know is naive. And then hopefully computation gets easier. So what is that assumption? What is that naive assumption that you are making? So the problem is these values. What happens if I don't have 2 values? Can I still apply it? Yes, you can. Because it's still individually you can say this belongs to this or yes or no. So attributes or features are conditionally independent. So attributes are conditionally independent. What is that supposed to mean? Well, are sunny days somehow depending on overcast? Are rainy days depending on sunny days? Have smoking and diet something together in common? So are they completely independent or not? Or they are somehow correlated? So we talked about correlation. We started actually with correlation. So do they change together or not? So we are assuming that they are conditionally independent. So they do not depend on each other. If that's the case, then we can say that the probability of A1, A2, up to AN given V sub j, which is a classification value. So if I have some attributes that I know, so I eat a lot of fat, I smoke, I don't have physical activities, I am above 50, so will I get cancer or not? So the attributes, the features that give me the classification. So if that's the case, do you remember the sum rule and the product rule? How can I write this? Oh, if they are dependent, then oh my God, so the probability of A and B and A or B. So this is A, and A. So this is A1 and A2 and A3 and AM. If I do it with those rules, I'm gonna be dead. That's not gonna work. So, but if they are conditionally independent, I don't need that subtractive term in the set of rules. So then I will write this as, okay, this is the product of over I, the probability of A sub I given V sub j. So I can break it down because there is no conditional probability. So what is the probability of A and B? What is the probability of A or B? I need to know whether they are depending on each other or not. Or they are operating, the attributes are operating completely independent from each other. If I make that assumption that they are conditionally independent, then I can break it down. The worlds become really, really beautiful because I don't need to subtract anything. I don't need to add anything. So the probability that I have a bad diet and I'm smoking and I get cancer given that somebody had cancer is the probability of smoking given cancer times the probability of bad diet given cancer. So I can just multiply them. You can just multiply, yeah, because they are independent. So I don't need any corrective term because they are independent. And that's exactly this conditional independence, that's what makes us naive. Because of course in the reality everything is depending on everything else. You just don't know. You are walking through the floor and you are affecting the life of other people. If somebody sees you and says, oh my God, this guy is so handsome, I'm looking ugly. So you are affecting other people and you don't even know. So we are assuming that things are conditionally independent is extremely naive because things depend on each other. But if we make it work, nobody cares. I don't know why people don't say that because it doesn't sound scientific, right? It doesn't sound scientific. We don't care. But we don't care because it's working. And we really do everything to maintain that scientific image. one of the difficulties right now to get pathologists using digital technology is we have 400 years of history of using microscopes. Now you can get rid of the microscope, buy a digital scanner, and you have your images. You can use computer vision. You can use AI. They don't do it. Why? Because having a white coat and a microscope and you stay there and you make a photo of yourself is not the same as standing in front of the display. Display is not science. Microscope is science. So we maintain that image. So the variable x, these sort of things affect us. I'm not insane when I, from time to time, say examples like this, because scientists are people. They are governed by the same rules as everybody else in the society. So variable x has some features or attributes, if you want to call them attributes, A1, A2, up to AN. Now we are asking what is the most probable value of f of x. What is f of x? Well, that f of x that we started with, and we said there is a relationship between an in and output. Nobody knows that relationship. Can I use this approach to estimate, to approximate that function? Artificial intelligence is function approximation in a very sophisticated way. So then we say, yes, you can. So the value of, let's say, maximum a posteriori, let's go back to MAP. I know, we said is exhaustive. What do we want to make it? We want to make it easier. With argmax, V sub j coming from the capital V, the set of all values, the probability of V sub j given A1, A2, AN. So now I want to reformulate it. Now I want to use probabilities for classification or for function approximation. So what is the probability of a given classification, any classification, or any value for that matter, if my instance is described by a set of features back to the origin of AI? I have some attributes, some features, I want to classify them. Even if you have 5,000, okay, I'll apply PCA first, I get the 20 principal components, and then I work with them. So, and of course, we will then use the Bayes theorem to rewrite this. So this is the argmax, argmax V sub j coming from capital V, and we write the probability of A1, A2, A sub n given V sub j times the probability of V sub j over the probability of A1, A2, up to AN. The same thing. So I'm rewriting the probability, the Bayes theorem, but this time I'm using features. So I'm using features, and my output is the classification or the value of the function. And again, this is constant. The probability of features are constant. This is my data. This is the evidence. The data directly or implicitly through the features, that's still the same. So this is argmax V sub j coming from the capital V, the probability of A1, A2, up to A sub n given Vj times the probability of Vj. How many times I had that classification? So, okay, but this is still exhaustive. This is still not doable. Because if I really want to calculate this, I have to use the sum product and rule product and apply it and do correction, and I need to know who is depending on who. I need to observe those conditional probabilities, and I don't have them. I'm barely getting some data. So I make the assumption that they are conditionally independent. A1, A2, A3, up to AN, whatever features you have that are describing your data, they don't have anything to do with each other. The horsepower of the car has nothing to do with the weight of the car. Do you see the problem? The horsepower of the car has nothing to do with the weight of the car? Of course it does. Yeah, but let's assume it doesn't. That would be naive. I know. So let's call it naive. Scientists are funny that way. So they can turn the negative things to become their trademark. You call me naive, I call myself naive. Okay. So if we want to do the V of naive Bayes and B, so instead of MAP, so this is still MAP. This is the difficulty. We cannot do this. We cannot do this. If you still have difficulty to follow me, go back to the sum rule and product rule and say, how can I calculate this if I have 500 features? We cannot do this. We don't even know the dependencies. How do you want to find out the dependencies? You need infinite number of observations. There is no such a data. So the V of NB will be still argmax. V sub j coming from the set of capital V. P dot Vj will come out. And instead of sum, I will get a product over I, the probability of A sub I given V sub j. So that's this formulation if I assume this. So if I assume things have nothing to do with each other. And this is our naive Bayes classifier. Now I have something that I can run. Now I have something that it doesn't need to be exhaustive. I'm not going over the set of, did you see what happened? I'm not going the set of over set of all possible solutions. I'm going over set of all possible values for the classification, which is most of the time 2, 3, 4, 5. So it's not a million. I can do exhaustive here. But you still are naive. I know. Relax. It's working. I show you the results. But the conditional independence is often violated. Nonetheless, it works. It's working. I made a harsh assumption. I made an audacious assumption. And this is what it takes to be a really good scientist. You have to do something that everybody says, are you insane? You cannot do this. How do you think most of the discoveries happened? People go insane. People think, so everybody is telling you, you have to think outside of the box. But if you think outside of the box, they will hunt you down, and they will punish you. Because you did think outside of the box. The box is sacred. You should not go outside of the box. So we say it. That's a lip service. Please realize this as young engineers who are about to go out in the wide world and do whatever. We say that we appreciate new ideas. We don't. We don't. If you have a new idea, people will fight you. People will discredit you. People will write papers to reject your papers. how empty your life should have been to write a paper to reject somebody else's paper. Just so, how much time do we have? We have a little bit of time. That's good. So don't forget, you need a lot of probabilities. You need a lot of data. If you don't have those observations, that's not going to work. We need the data. So still, with all the tricks, we need the data. Okay. Now, using training data, estimate the probability of Vj, which is a value or a class, and the probability of A sub I given V sub j. So we have that beautiful, this is one of the beautiful equations we have. It just looks amazing, looks sophisticated, looks slick. A lot of human knowledge behind this. You should appreciate this type of equations. You can just print it, put it on top of your desk or something so that, look. But still, I have to do a lot of work to get those probabilities. That's an empty framework. What makes it to come alive is the data. So we need the data. How do we do that? So what would be the potential problem? What would be the potential problem to get those data? So if I want to estimate that probability of A sub I given V sub j, what would happen if that estimate is 0? What would happen if that estimate is 0? One of them is 0, everything is gone. What? The entire mighty palace of the god of probability collapses if one value is 0. Yeah, then we should not let anybody get a value of 0. That's unfair. Everybody should be treated fairly. Non-zero. Oh, well, but how you do that? So if, for example, no value for this A sub I is assigned to the target V sub j. So if no value is assigned to V sub j, just for one of them, boom, that product is 0. No decision making possible. I have 500 features, one of them is 0, I cannot work. Is that a reliable solution? Well, look, it seems we have difficulty to understand the concept of probability. Because concept of probability is infinite observation. If you infinitely observe, nobody is 0. But I cannot infinitely observe. I know. So we have to come up with another solution, which may be also naive. So let me see, we have time in the 1 minute. Okay, so I give you that and maybe we talk about it. So one of the things that we do, we sit down and think about this and say, look, this cannot work. No, I'm not even at the moment thinking about a complete algorithm. We just came up with an equation that is doable, is not going over all possible solutions. It is going over all possible class values, make it very friendly. But since I replace sort of my sum sign with product sign. If one of these guys is 0, everything is gone. So I cannot even start thinking about an algorithm. How do I learn as a naive Bayes classifier? Because I have to take care of this. One of the things that we do, we sit down and say, you know what? Then a better estimate would be something like this. I sit down and experiment on the paper with some sort of rational estimate. A better estimate would be that the probability of the estimated probability of A sub I given V sub j would be NC plus MP over N plus M. And NC is the number of cases with V equal V sub j and A equal A sub I. And N is the number of cases with V equal V sub j. And M is a weight assigned to the prior, to what you know. And P is the probability, the prior estimated based on data. So we sit down and come up with something that if you, so this could be the problem. If this guy is actually 0, then I want to have something that's still working. So, which means we come up with a basically heuristic. Who said I should do it this way? Nobody. Do you have any other solution? No? So how do you know this works? Well, I plugged it in, it's working. Again, the working argument, which is the empirical evidence. Don't underestimate the empirical evidence. So I sit down, come up with something that makes sense, and I can plug in any number. So I come up basically with a weighted version of my probabilities and take into the account my nightmare that if it is 0, I don't get 0. I get something. So we do another trick. So we will talk about this because we have to go through an example, and I want to see the algorithm of naive Bayes learning really work, give us something in total, just to give you the idea how much challenge we have to overcome to establish the foundation of naive Bayes, which is a fantastic foundation. And we use all this, we assume that's correct, and we hopefully go through an example on Thursday. And after that, we will have the midterm exam.